Statistical distributions.
Yes, statistical distributions is the next, no?
Yeah, session 3 is statistical distributions and their applications, advanced control charts, process capability, and all that.
Yeah, right.
Okay. So let's start. In fact, this should come before control charts, you know.
Right.
Next time you
Yeah.
change the sequence.
Correct.
Statistical distribution should come before control charts, you know.
Correct.
Because we are applying control, these distributions and control charts, na?
Right.
Okay. Now, let's talk about statistical distributions. We are talking of chapter 20 now. Chapter 20.
Chapter number 20. Okay.
Yes. Chapter number 20. Yes. Shall we move on?
Yes, sir.
Okay. So basically, for today's portion, we'll be talking of 3 distributions. Basic statistical distributions come under 2 categories. One for discrete statistical distribution, that is for attribute quality characteristics. Other is continuous statistical distribution for measurement, normal quality, all measurable quality characteristics. As we talked about, 2 important areas. Now, on discrete statistical distributions, we'll be talking about 2 things. One is binomial, and discrete statistical distributions for attribute quality characteristics, and continuous statistical distribution for measurable quality characteristics. For this discrete, we'll be talking of binomial and Poisson, and for continuous, we'll be only talking of normal. For negative exponential, student C chi-square A, we'll be talking for paper 5, when some of you, I understand all of you are appearing for that, except I think Dr. Kallani, all of you are appearing. So there we'll be talking about this negative exponential, students T chi-square and F distribution, which will be necessary for our tests of hypothesis very much. Now coming to binomial distribution, you know, we must understand binomial and Poisson, the conditions of validity first. Binomial distributions have 4 conditions of validity. First is the binary classification. Defective, non-defective. Machine utilized, not utilized. If underutilized, then it will be trinomial. If it is number of areas, then it will be multinomial. So it's a binomial distribution. 4 conditions of validity. It's a binary classification. Okay, effective, non-defective, male, female, utilization or non-utilization, not underutilization, and then user of the brand, non-user of the brand, then efficient, inefficient, and all that. Okay, binary classification. Second is sample size n is known and is finite. How many items you are inspecting, you know. How many, what is the sample size, you know. So sample size n is known and finite. Third is chance of success or failure remains constant from one trial to another. That is P. You don't tell the people that all of you will get an umbrella if you come every day in this week. Or you don't take a utilization of the machine when the boss is taking around. They'll be biased. Or find out the rejection in a machine when some important raw materials are being used. So under normal conditions, this has to be taken. Okay. And finally, trials are independent. These are the 4 conditions of validity of binomial distribution. And sample size, when it is n, the number of defectives can be 0, 1, 2, 3, up to n. So n plus 1. So the distribution is probability x equal to r is NCR, P to the power r, Q to the power n minus r, and r running from 0 to n. Mean of this distribution is NP, n into p. Variance of distribution is NPQ. Q is 1 minus p. Okay. So there's a very simple thing. You see here, probability x equal to r is NCR, P to the power r, Q to the power n minus r. are running from 0, 1, 2, 3 up to n, and where Q is equal to 1 minus P is the population proportion of good items. The average distribution is NP and the variance is NPQ. That is NP to 1 minus P. Accordingly, the control charts will be NP bar will be, P bar is overall average, will be the central line. NP bar plus or minus 3 times square root of NP bar into Q bar will be the upper control and lower control limits. You see, homogeneous proportion of defectives you have to find out. Where is it applicable? Rejection, rework, downtime, utilization, absenteeism, market share, etc. are governed by binomial distribution. You must understand these conditions of validity and where is it applicable. Okay. And we have already seen a control chart of this one, where number of defectives were seen. All 20 samples of 10 were inspected and number of defectives were there. And we knew how to calculate the overall average or overall variability, and then how to homogenize that, how to eliminating the out of control points, you homogenize the data. Okay, this is the binomial probability distribution, binomial pattern. Okay, next we'll go into Poisson distribution. Here the conditions of validity are where there is a large area of opportunity for the event to happen, event to occur, but the chance of its actual happening is very, very small. We get a Poisson pattern. Okay, stockouts, breakdowns, accidents, customer complaint, defects like blowhole. You see, a blowhole in a casting is a defect, not a defective. Whereas a crack in the casting is a defective. In blowhole in castings, bubbles in glass is a defect, whereas the crack in the glass is a defective. Pinholes in tin plate, then black spots in capsule, etc. follow this pattern. Okay. Here the probability distribution is probability x equal to r. Next one, probability x equal to r e to the power minus lambda, lambda to the power r by r factorial. R running from 0, 1, 2, 3 up to infinity. You see, lambda is the average number of defects per 100, average number of complaints per month, average number of stockouts per quarter, average number of accidents per year, and so therefore that is lambda. Okay, probability. And where lambda is the average number of customer complaints per month, or average number of stockouts per year, or average number of accidents per quarter, or average number of breakdowns per week. And so you have to mention the period or this one number. Okay, this is how the Poisson. Mean of this distribution is lambda. Variance is also equal to lambda. Is the only, mean of the distribution lambda, and variance is also distribution of this distribution lambda. No, it's the only discrete statistical distribution where mean equal to variance. Here, for a control chart, central line will be lambda bar, overall average. And control limits will be lambda bar plus minus 3 into square root of lambda bar, because it is always 3 times the standard deviation, and lambda is the variance, so square root of that will be standard deviation. Well, lambda bar is the average number of customer complaints per month, or average number of accidents per year, or average number of blowholes in a casting, etc. Okay, so that's how we calculated our limits initially in our last session, and also we homogenize the data and try to find out the homogenized average for future controls. Homogenized control limits for future controls. Okay, so this is the applicability of Poisson distribution. So these are the two distributions in discrete statistical distributions which we wanted to cover to you. The only continuous statistical distribution we'll be covering to you, the exercise and Poisson distribution we have given here.
That we can refer to the book, sir, for that exercise.
Yeah.
The distributions.
Sure. This is chapter 20.
20, yeah. And first we take the binomial, right?
Okay. Take the applicability 3.4. Yeah. First, you take the binomial distribution.
Yeah. So there are worked out examples here.
There are worked out examples here. So you can refer that. This is 2.5.1 to 3.5.1, 3.5, page 20-4, page 20-4.
Okay.
There are 3 examples worked out. I don't want to, 4 examples. 5 examples worked out. I don't want to unnecessarily worry you here. You go through it. In case any problem is there or you don't understand, tomorrow you can tell me. You see, tomorrow we can clarify them. Okay.
Okay.
Similarly, Poisson distributions. We have talked about conditions of validity, mean, variance, and all that. Here I'll give you a simple example. You say here, page 20-6, 4.4, exercise on Poisson distribution. This is important. Suppose a car hiring concern has 5 operating cars. Average demand comes to say 3 per day. Okay. So problem is how many days you will have no demand, number 1. And number 2 is how many days you will refuse demand. No demand means R equal to 0. So e to the lambda is a 3 here. So R equal to 0 means e to the power minus 3. That is about 0.4. That will be covered. That will be seen in table number 2, Poisson table. Okay. Go for statistical table number 2. Statistical table number 2. Go to page number. Yeah. Lambda is equal to 3, na?
Page number क्या है sir? ST2.
I'll tell you page number. Statistical term number 2. Page number 30-40. 30-40.
30-46.
30-46, correct. 30-46.
Hmm.
Okay. Lambda equal to 3. Lambda equal to 3. That is, it will be 30-45, I think. Yeah. 30-44. Lambda equal to 3. R equal to 0 is 0.498. 0.498. Roughly 5%. So 5% of the time, roughly, you will not have any demand of cars. All the 5 cars will be idle. On 5% or 4.98% of the time, you will have no demand. Okay. Now, what percentage of time you will refuse demand? That is, when the demand for cars is 6 and above, 6, 7, 8, 9, any number, then he will refuse demand, which is nothing but 6 to infinity. E to the power minus lambda, lambda to the power r by r factorial. But we cannot go on adding up to infinity. So what we do is 1 minus up to 5. 1 minus 0 to 5 e to the power minus lambda, lambda to the power e to the power minus 3, 3 to the power r by r factorial. Again, see this table for lambda equal to 3, r equal to 5. It is 9161. 9161 is a cumulative value. So 9161. So 1 minus 0.9161, roughly 0.09 or less than 10%. See, 9.64%, roughly 10%. So 5% of the time you will have no demand. 10% of the time you will have refused demand. You will refuse demand. Based on these values, you can take a decision. If the refusal is too much, then you will try to buy some car. If the no demand situation is more, then he will try, think of selling some car. So buying or selling strategy can be decided based on these figures, So that is why I wanted to give you some idea of this example, which is very important from that point of view. Similarly, you can work out the other examples. They are again very simple. They are worked out that way. Again, statistical table number 2 is used. Lambda values are given. Okay, so that is how you try to calculate. Hypergeometric will omit for the moment. Now we'll go to the most important statistical distribution, namely normal distribution. Okay, that is given in page 20-9. 20-9. Okay. Here, refer statistical table number 1, ST1. First table in statistics is normal distribution table, you see. Which is the most important statistical distributions all statisticians or quality controllers will have to use. Now let us work out what is the area up to plus minus 1. First find out what is the area up to 1, from minus infinity up to 1, 1.0. Let's work out. Can you see that? Can you refer that table ST1, page 30-40? Page 30-40, table, statistical table number 1, ST1. Now this is a normal distribution with mean 0 and standard deviation 1, which we call standard normal distribution. Normal 0, 1. What is the area up to 1? Any of you can help me? 8413. Have you seen that? Just see your table. All of you have the book?
Yes, sir.
किताब है ना आपके पास?
Yeah, that's first column is Z. So we have to see 1.0.
1.0, 1.00, that is 8413.
8413, the second column.
Yeah, second column.
Yeah.
First column is values.
Right.
And then the values which are given, there is second column actually, 8413. Okay?
Right.
That means what is the area to the right of that?
1 minus.
1 minus that, 15.1587. That is the area to the right of plus 1. Because of the symmetric nature of the curve, same area will be there to the left of minus 1 also. So 1587. So therefore, both sides, how much it will be now? 8587 plus, 1587 plus 1587. How much is that? 0.1587 plus 0.1587. That is 0.1587 into 2. Use your calculator. 0.15.
Sorry, sir. Ms.
Yeah.
Zankana, Ms.
Multiplied
Zankana,
by
are you
2.
around? Ms. Zankana? Hello?
3174.
Ms. Zankana, are you around?
Yes, sir. Yes, sir. Yes.
You have to answer. Why are you keeping quiet? It is for you.
Yeah.
You have to open the calculator, open the book, and answer to what sir is asking. What are you doing? Sorry.
Yeah, correct.
Calculating, and then I kind of.
I am around, but I am just listening to sir because I want to learn from him. You have to interact, please.
Yes,
Correct.
sir.
Otherwise, it will not be it will be just sitting quietly and no benefit you will get.
These are very, very valuable things which no one will teach you. This is very, very, very valuable. So please make use of his wisdom and knowledge.
Correct.
Please, Zankana, please.
Sure, sir.
Okay. So what is the area now? This is 0.3174. 0.3174. Now, so what will be the area in between 1 plus minus 1, 1 minus 3184. So how much is that? 1 minus 0.3184. Calculate that. 1 minus 0.3174. That is 6826. 0.6826. What does it mean? 68.26% of the observations will lie within plus minus 1 sigma for a normal distribution. Just to conceptualize, suppose the average height of adult males in India, average height is 5 feet 6 inches. And standard deviation on height is 2 inches. That means you add 1 time standard deviation, that is 5 feet 8 inches, and subtract 1 time standard deviation, 5 feet 4 inches. That is 68.26% of adult males in India will have height between 5 feet 4 inches to 5 feet 8 inches. In industry, similar thing happens. You have calculated the average and standard deviation. Average plus minus 1 standard deviation will cover 68.26% of the observations. Okay. Let's go to 2 sigma. This is 1 sigma. Let's go to 2 sigma. What is the area up to 2? Just refer the table again. Up to 2. Yeah, any of you? Yes, Kalani? Up to 2, 2.0, same table. 30-40, statistical table number 1. Up to 2, what is the area? 2.0, 2.00.
Yeah, नरेंद्र आप भी बता सकते हैं, just.
Yeah.
सर
Any
आपको
of
आप
you?
दोनों को पूछ रहे हैं, we are other observers.
Sir, 0.9772.
Very good. 9772. So what is the area to the right of that? 0.0228.
Yes, sir, 0.0228.
8. Okay, 1 minus that. Same area will be there to the left of minus 1, minus 2. 0.228. 0.228. So what is the total? 0.228 into 2. 0.0456. So 1 minus that, what will be that? 1 minus 0.0456 equal to 9544. 9544. That is, you add one more standard deviation, 5 feet 8 inches, 5 feet 10 inches, and subtract one more standard deviation, 5 feet 2 inches. 95.44% of adult males in India will have height between 5 feet 2 inches to 5 feet 8 inches. Okay. So this is the, similarly, any problem you have in industry or your tissue culture, you have some, this one, measurable quality characteristic, height of the plant and all that, you can apply the same thing. What percentage of the height of the tissue culture will have the height between this and this, you see? Okay. Similarly, any chemicals you order will have this. So finally going to 3 sigma. So what is the area up to 3? 3.00? Yes. Akanksha, what is the area up to 3?
39.74.
Yeah. Go to next page. 30-41. Up to 3. 3.00. How much is the area?
9987, sir.
Right. 9987. So the area to the right of that will be 0.0013. 0013. Okay. Because of the symmetric nature of the curve, same area will be there to the left of -3 also. 0.0013. So the area in between will be 1 minus twice of that, 0.0026. That is 0.9974. 9974. So now the same way, height example, if you take 6 feet here, 5 feet here, 99.74% of adult males in India will have height between 5 feet to 6 feet. You see, in your tissue culture, same thing will happen. In your raw material, any measurable quality characteristics, same thing will happen. Okay. Therefore, plus minus 1 sigma covers 68.26%, plus minus 2 sigma covers 95.548% of the observations, and 3 sigma covers 99.74% of the observations, okay, of the population. So this is a very important learning you should have, and you should always, normal distribution is one thing where you have to have a full grip on that, on this one. So this is what is given in page 20-9, okay? Okay. Let us work out a simple example,
okay,
so that you will understand its applicability. Go to page 20-12. 20-12. Example 3.1. Example 14. 6.2.1. Suppose scores in MMS entrance test in particular year was, mean was 63 and standard deviation was 3. What percentage of students will score 66 and above? Okay, 66 and above. Now, if there are 800 seats available and 80,000 candidates apply, what will be the cutoff score? 800 seats available, and this is all India competition for Masters in Management Studies. 80,000 candidates, what percentage will get seats? 800 by 8,000, that is what percentage? Yes, doctor? What percentage, Lani?
1 by 10%.
Yes, hardly 1%. No, 800 by 80,000 is 1%. 1% only will get seats. Right? Is what is given here. Probability X less than or equal, greater than or equal to 66 is X minus average by standard deviation. That is 66 minus 63 by 3. That is 1. And beyond 1 sigma is 15.87. So 15.87% of the candidates will score 66 and above. Next one is more important. That is your probability less. Suppose the cutoff score is U. Then probability less than or equal to U is 800 by 80,000. That is 0.01, 1%. So X minus average by standard deviation is U minus average is 63, standard deviation is 3, is equal to 0.01. Therefore, normal 0.1 is equal to U minus 63 by 3. Now, 0.01 will be corresponding to what value? Just look at table 0.01. That is 99.9%. Yes, Harsha?
yeah.
99%. So that is 2.33. 2.33. That is U minus 63 by 3 will be equal to 2.33, which gives you U equal to roughly 70. So if somebody scores 70 and above, then there is a large, high chance of it getting admission in the MMS entrance test. Okay. So this is very important because given the past data, average and standard deviation you calculate, and then you can find out what percentage will be going beyond the specifications. And if more percentage is going beyond the specifications, then what to do, we shall talk about tomorrow, the Jishu-Hossain and 5S and all that, how to reduce the variability, that we'll be talking more about tomorrow. Okay. And this example is pictorially demonstrated is 20-13, page 20-13. This is one example which you have to understand very thoroughly. Another example which you have to understand very thoroughly is 6.2.2, example 15. Okay, further application of normal distribution. See, this is a problem I faced in my earlier job. Thickness of aluminum sheets in millimeter and percentage of sheets they're given, From there, you can calculate the average and standard deviation. Average comes to 0.2294 mm and standard deviation comes to 0.01 mm. Okay. Now the question you read. Can some of you read the question? Yeah, that is page 20-14. 20-14. First sentence, question number. Read that question. Yes.
Yeah. Harsha,
Harsha or Akanksha or whoever is there.
Yes, sir.
Go ahead.
20
Determine.
14, right?
Yeah. 20-14, first question.
The example.
First sentence.
Example 16.
First sentence read.
Determine. Okay. Determine percentage of aluminum sheets which will
Yeah,
have
determine.
thickness less than or equal to 8.
8.5 thou, that is 0.2159 millimeter. Okay. So this will be given by probability x less than or equal to 0.2159. Now you have to normalize, subtract the mean and divide by the standard deviation. Mean is 2294, standard deviation 0.01. So that comes to probability normal 0.1 less than or equal to minus 1.25. Because of the symmetric nature of the normal distribution, area to the left of any negative value will be same as 1 minus area up to the positive value, So minus 1.25 will be nothing but 1 minus area up to 1.35. Okay. Remember, P of minus U is 1 minus PU. Remember that. Write down somewhere. P of minus U, the area up to any negative value is 1 minus P of plus U. 1 minus, that is 1 minus area up that positive value. Okay. Now refer the normal table up to 1 point. Yeah. Refer the normal table up to 1 point. How much is the area comes to? That is 0.2159 minus the average you are trying to work out, 0.01 is equal to 0.025. Okay. Where from the 0.25 come? Because 2.5% will be below that. Now refer the table. How much the area comes?
At 1.35, Z value of 1.35.
Yeah. What is the area comes?
आपको मिला ये टेबल 30-40 पेज नंबर 30-40 पे
30. Yeah. How much is the area there?
Z value 1.35. So Can you see the 1.35 ka corresponding area?
0.9115.
Yes.
Yeah.
0.9115.
Yeah,
Yeah.
0.9115, correct.
Okay.
Which one you're talking?
That 1.35 Z value,
Yeah.
you know, the area is 0.9115
Yeah.
towards the left of this value, and towards the right will be 1 minus that. You know, and since it is a symmetrical distribution.
Which problem you are referring to? I'm getting lost.
So this is same you are referring to, that is page 2014 May. The top one, you know, determine percentage of aluminum sheets which will have thickness less than or equal to 8 thou.
Acha, okay.
So, you know, the Z value was worked out as minus
1.35.
1.35, you know. So
1 minus area up to 1.35. What is the area up to 1.35?
Up to 1.35 is 9115, 0.9115.
Right. So 1 minus that area.
Yeah. So
9115, right?
yeah.
You're right.
So it comes
which is equal to
0885.
0885. That 8.85%
Yeah.
will be falling below that. Okay. 8.85% will be falling below that. Okay.
Right.
So that is how you have to calculate the value. Okay.
Right.
This is how the normal distributions we make use of. For the next thing, we have to talk about the process capability. Na?
Yeah, that's right.
Okay, let's go to the next chapter. What is process capability?
What is the chapter number?
Yeah, chapter number 21.
Process capability.
The 22.
22, page number
Yeah, 22.
22-1. Page, chapter 22, we are at chapter 22, you see.
Right.
Process capability and capability ratio. When a range chart of variables shows a process to be in control, the pattern of variation of individual products can be taken to be stable. Process capability is defined by 6 times standard deviation, plus 3 times standard deviation on the plus side, minus 3 times standard deviation on the minus side. So plus minus 3 sigma, that is 6 sigma, you see. And R bar is the homogenized range, and that is, and D2 is a constant, which is given in statistical table number 6, you know. Now, process capability is the inherent, you write down, is the inherent process variability. Inherent process variability, that is variability observed in the process, influenced by chance or common causes only. Variability observed in the process, influenced by chance or common causes only. If there are assignable or special causes, it cannot talk of capability. You cannot talk of capability of a madman. He will be very nice to you for some time. Next moment, he will hit you. Therefore, first you must bring stability. How to bring stability? Through Jishuhosen, which you shall talk tomorrow. Okay? Because I was calculating process capability just like taking data, R-bar, D2 and all that. Before I went to Japan, you know. After I went there, I saw what I was doing so long. The American way of teaching was totally not practically applicable unless there is stability in the process. So first you have to do 5S, which is outside sort of cleaning, oiling, straightening, tightening, and then you have to do Jishuhosen, you know, that is autonomous maintenance. Tomorrow we shall talk about this. So you have to bring the stable process. Process has to be brought stable. Stability in the process must come. Then only you talk about capability. Okay. So process capability is the inherent process variability. There is variability observed in the process, influenced by chance or common causes also. Okay, and this will be quantified by process capability 6 times R bar by D2. Sigma is estimated from R bar by D2. This is the control charts. We estimate sigma, and for a long-term distributions, when you pattern you have, we estimate sigma from S, small s, where S square is 1 by n minus 1 sigma xi minus x bar whole square. So these are the critical. Suppose L tolerance is equal to 6 times standard deviation. Then optimum set point will be L plus U by 2. Right side jayega to it will go above U, left side jayega to it will go below L. If tolerance is much higher than the 6 sigma process capability, then you have a much wider window to operate. Whereas in India, we have got most of the machines where process is not able to meet the tolerance. So that is picture number 3, when tolerance is much lower than the specifications. You see? So there, the optimum set point will be to try to minimize this cost of scrap plus rework. And their optimum set point will be L plus U by 2. L is the lower specification limit, U is the upper specification limit. L plus U by 2 minus sigma square by T log E C2 by C1, where C1 is the cost of an item falling below L and C2 is the cost of an item above U. This you need not have to worry. You worry about the first one first, that is this one. Okay. So we shall now work out some problems and then see how that we have to work it out. Go to page number 2. So CP, CP is short-term capability index. Is tolerance voice of customer divided by voice of process. T by 6 sigma. Next one, Santosh, let us see, is there. T by 6 sigma, Yeah. You see here, measures of precision, CP, is voice of customer, T, tolerance, U minus L, upper specification minus lower specification is the voice of customer. And 6 sigma estimated from R bar by D2, that will be the voice of process. Voice of customer by voice of process gives you the measure of precision. Measure of accuracy will be given by minimum of X double bar minus, this will be X double bar minus L by 3 sigma R bar by D2. Sigma estimated from R by D2 minus U minus X double bar by 3 sigma R bar by D2. So L is the lower specification limit and U is the upper specification limit. T is equal to U minus L, upper specification minus lower specification. That is known as the tolerance, And X double bar is the overall process working level. Note, CP will be always greater than equal to CPK. Ideal value is CP is equal to CPK. Okay, so that you must remember. That is the short-term capability index. Now we go to long-term performance index. Next one, let's see. Is there long-term performance index, that is PP and PPK. Okay, let's work out this example. This example is given in page 22-11, example 4. 22-11, example 4. This is computation of CP and CPK and their interpretation. Computation of CP and CPK and their interpretation. Okay. All of you open that. Can some of you read that question?
Yes,
One of you read that question.
that example 4 you are talking.
Example 9.4, example 4, yeah.
Okay.
Computation of CP and CPK
Yeah.
and their
Yeah.
interpretation.
Right.
Yeah,
right.
some of you read that.
So now Zankana madam आप पढ़ सकते हैं?
So this is not the problem. Let us see that problem is there or not. See whether that
we'll go
problem
with
is there.
the book only, sir. What you are
Yeah,
saying.
it's in the book. Refer the
Yeah.
book. Yeah.
Refer the book. We refer to the book.
Refer the book. Right. Go ahead. Some of you read that, please.
Zankana madam.
Sir, I'm reading.
Yeah.
My
Yeah, please.
specification on door ID of an item was 50 plus minus 0.003 mm. After summarizing control chart data, it was found average range of two samples of size was 2.3 microns and overall average working level was 49.998 mm. If one range was 14 microns, which is equal to 0.014 mm, use CP and Statistical values and interpret them.
Yeah. Now, clear? Now, here the specification is given as 50 plus minus 0.003. The upper specification 50.003. Lower specification is 49.997 mm. So tolerance is upper specification minus lower specification, that is 0.006 mm. Okay, that is the first thing. Overall average working level X double bar 49.998 mm. Okay, upper here lower specification 49.997, upper specification 50.003. So tolerance is 0.006 mm. Overall average is 49.998 mm. R bar is equal to 2.3 mm is equal to 0.0023 mm. 2.3 micron, that is 0.003 mm, 0023 mm. Now for range chart, central line is R bar, that is 0.0023 mm. Upper control limit is D4 R bar. Here n equal to how much? N was given as 6, the?
Right.
Yeah, n was 6. So refer the table, statistical table number 6. And what is the D3 and D4 value? Tell me. Statistical table number 6, you refer that. Yeah, n equal to 6. What is capital D3 and capital D4? Any of you can help me? What is D3 value? Statistical table number 6, page 30-30, 55, 30-55. Yeah.
Sir, 0.
D3 is 0, right? At D4,
2.004, sir.
2.004. Right, you are right. N equal to 6. Very good. So you want D3 lower control limit will be equal to 0 and upper control limit is D4 R bar is 2.004 multiplied by R bar is 0.023, that is 0.00461 mm. Okay, that is the calculation which is shown there. Okay, now go to the next page. Page number 22-12. Okay. Since one range was 14 microns, now we have to homogenize that. Total range is 0.023 minus that 0.014. Okay. 0.023 into 30 because there are 30 ranges. Nah?
Yeah.
This is the average. So total will be 30 into this minus 0.14 divided by 30 minus 1 because one range was out of control. And that is equal to 0.0019 mm. Okay. So process capability now is 6 R bar dash by D2, 6 into 0.0019 divided by. Now, what is the D2 value for n equal to 6? Again, refer the same table. Small d2. D2 value is, how much is small d2 value? N equal to 6.
So 2.534.
2.534.
534.
You are right, sir. 2.534. And that is what is divided there. 2.534. And that is equal to 0.0467. So CP, now measure of precision, is voice of customer divided by voice of process. T by process capability. T by 6 sigma. 0.006 divided by 0.0461. That is equal to 1.33. Now, as whenever it is more than 1, the process is well capable of meeting the tolerance. More than 1 it is, better it is. So, process is capable of meeting the tolerance. Now, let us try to see. So, management has given a good machine. Now, let us try to see how supervisors are running. That will be judged by CPK, measure of accuracy. That will be given by minimum of X double bar minus L by 3 times standard deviation and U minus X double lower specification and upper specification 50.003 minus 49 point this one minus X bar by 0.00223, which is equal to minimum of 0.44 and 2.22, that is 0.44. As it is less, very much less, that shows that process needs centering. So supervisors are not running the job properly. Though management has given a good machine, supervisors are not running it properly. You see? So this is a very important sort of decision we take based on the calculations and how the process is running. So CP will be always greater than or equal to CPK. And now let us try to see, all of you are clear of this? This is a very important example and it's definitely going to come similar example in the exam. Okay. And this is a short-term capability index. Now let us try to see. No, hold on. Let us complete the long-term performance index also, Santosh. Shall you complete that? Yeah. Now, the next one is, sorry, PP and PPK. That is given in 10.1, page 22-12. Sorry. Can some of you read that? Example 5. I'll interpret for you and read that.
Yes, sir.
Yeah, read it. Read it.
From analysis of past 6 month data,
Yeah.
average turnaround time at ICU in a hospital
Yeah.
was found to be 26.2
Yeah.
minutes and standard deviation was estimated as 1.35 minutes.
Right.
So if the management has set a target of 25 plus minus 5 minutes,
Yeah.
estimate process capability, compute PP and PPK
Yeah.
values and interpret them.
Now answer you read out here X bar.
Yes, sir.
Sorry, how much is the average? 26.2 minutes.
Yes, sir.
And standard deviation is estimated at 1.35 minutes.
Minutes.
Okay. Upper specification is 30 minutes.
40
Lower
minutes.
specification is
20 minutes.
20 minutes. Giving tolerance as U minus L is equal to
10
10 minutes. Okay. Now read that. Process
No.
capability is 6 times standard deviation, 6 times 1.35 is equal to 8.1 minutes.
Yes,
So
sir.
PP will be equal to T by 6 sigma, voice of customer by voice of process is equal to 10 by 8.1, 1.22. That means process is capable of meeting the tolerance. Okay.
Yes, sir.
Now let's try to find out whether we are doing the job correctly. Now here individual. Now let's find out the PPK value, which is minimum of X bar minus L by 3 sigma and U minus X bar by 3 sigma. And that comes to work out to 0.94, which is less than 1. That means PPK value is not being maintained properly. So the supervisors have to really work hard to meet the management commitment of the hospital. You see, again, you remember PP will be greater than or equal to PPK. Ideal value will be PP minus PPK equal to 0. This is long-term capability index. CP and CPK are short-term performance index. Okay, remember that. And PP and PPK will be long-term capability index. Yes, Santosh. Now you can take the examples. Santosh, take the examples, please. Exercises. Santosh, are you there?
Stop, stop.
Yeah, Santosh, take the exercises. Yeah. Process capability analysis. Yes. This just now worked out 50 plus minus 0.03, 4 ID. We have just worked out. Then, yeah, this also we have worked out. ICU example you have just worked out. Yeah, what are you doing? ये तो हो गया रे, ये तो किया ना सुबह कंट्रोल चार्ट्स. Yeah, go ahead, go ahead. आगे. So this is we have done 21, 22. You see, we have done that for the 23. We have done 22. We have done 23. You take 23. We have done that for Poisson distribution. 24 is MMS entrance test. We have done that. 24 is also MMS entrance test done. 25 is thickness of aluminium. We have done. Okay. So most of the examples we have worked out already. आगे जाओ, आगे बढ़ो. What is the next chapter we have to cover? Correlation. Car hiring concern. Instead of 5 cars, I have given the 6 operating cars. You see, that is what I told you. There will be in the exam there will be difference. You cannot just copy from the book. There are 5 cars I gave you. Here I have given 6 operating cars.
Right.
Okay.
So they can refer to the book, you know,
Yeah, you can refer to
open
the
book
book.
exam.
Yeah,
And,
refer to the book. But then time won't be sufficient. Best
Time
thing
will
is,
not be sufficient unless they have practiced enough, you know.
yeah,
They
you
will not be
practice
able to
them,
complete.
practice the examples of the book,
Right.
and then come
Right.
in the hall with the calculator and with clear understanding of what you will do.
Right. So that this completes the chapter, sir. And there's something on the advanced control charts which you can take after the, or we will break after 10 minutes. So in the in 10 minutes time, maybe you can
Okay.
cover the advanced control charts.
Advanced control chart में क्या है? What is to be covered?
You know, there's a chapter on that.
I know, but there we have already covered, na?
Yeah, they,
Process capability analysis and all that.
yeah. If anything is
देखो ना examples देखो, I'll make out.
नहीं एग्जाम उसमें से कोई क्वेश्चन सेट नहीं किया था लास्ट टाइम पे.
अच्छा, we have answered most of the questions.
That's right. So then shall we advanced topics on control charts में there were technical note basis for plus minus.
That is chapter
21.
21. Yeah, one thing I have to cover here
Yeah.
is repeatability and reproducibility.
Correct.
Open page 21-11, 21-11
Right.
and 21-10.
Right.
Okay. Now, can some of you read the definition of repeatability? Repeatability R, this is gauge R and R, repeatability and reproducibility. Okay. Please read that repeatability.
हर्षा मैडम आप पढ़िए अभी.
Yeah, read that.
So repeatability.
Yeah.
Repeatability is the variation in measurements obtained with one measurement instrument when
Yes.
used several times by one
Yeah.
appraiser while measuring the identical characteristic on the same part.
Have you understood now? Same
Yes.
measuring instrument, same appraiser, same part, same ambient, same sort of quality characteristic you are measuring, then you have repeatability. Okay, now read the reproducibility.
Reproducibility.
Yeah,
Reproducibility is the variation in the average of measurements made by different appraisers using the same measuring instrument when measuring the identical on the same part.
okay. Here only difference is different appraisers. Instrument is same, quality characteristic is same, parts are same, ambient is same, only different appraisers will be measuring that. Same component. Okay. So that is the difference in repeatability and reproducibility. Now I would request to read next page 4.1.5 and 4.1.6. Some of you read that. Somebody else can read or you can continue.
Okay. If repeatability is large compared to reproducibility.
Yeah, underline that. If repeatability is large compared to reproducibility, then what happens?
The reasons may be A,
Yeah,
the instrument needs maintenance.
okay.
The gauge should be redesigned to be more rigid. C, the clamping or location for gauging needs to be
Gauge. Yeah,
improved.
we normally pronounce the gauge.
Gauge. The clamping or location for gauging needs to be improved.
Yes.
Or there is successive within part variation.
Right? Understand that. So they will give you that this is repeatability or reproducibility. You have to understand which is repeatability, and then reproducibility you read similarly.
If reproducibility is large compared to repeatability,
Yes.
the possible causes could be A, the operator needs to be better trained in how to use and read the gauge instrument.
Yes.
Calibration on the gauge dial is not clear.
Right.
C, a fixture of some sort may be needed to help the operators use the gauge more consistently.
Right. Please remember that. So understand the definition of repeatability and reproducibility. And these two must be clear. The questions will come here. The repeatability is high compared to reproducibility, what is to be done? The reproducibility is high compared to repeatability, what is to be done? Okay. So not in the practical application questions, but in the principal questions, they will be coming there. One more thing you must understand is equally applicable for go-no-go gauges, and that is given in page 21-14, 21-14. The gauge R&R, repeatability and reproducibility is equally applicable to go-no-go gauges also. Yes or no, that you have to underline, and in your principal question that may come, you should be able to answer that properly. Okay, there is one thing gauge R&R, I wanted you to find out this one. The other thing which I want you to highlight, I want you to note, is this table 21-14, 21.1, where all these formulae are summarized. For P chart, you see, the overall average is P bar, standard deviation is P bar into 1 minus P bar by N. N is the sample size. So sometimes they will be asking you to calculate overall average and overall standard deviation. You must calculate P into 1 minus P by N. Square root of that will be the standard deviation. Okay, so that you must remember, because questions will come about the finding out the limits on that. You should be able to do that. Okay, and their applicability I have given for P chart, NP chart. I told you the applications are scrap, rework, downtime, utilization, absenteeism, then efficiency, market share, and all that. C chart similarly is given C bar plus minus 3 times square root of C bar. And here U bar by N. Here applicability I have given you is stockouts, customer complaints, breakdowns, accidents, and all that we have given. Then IMR chart, individual chart, I told you target plus or minus E2R bar. Okay, individuals, which is there. And then moving range chart, I have not talked to you. X bar chart, I have told you target plus or minus A2R bar. And R chart, D3R bar and D4R bar that I have told you. S chart, which S bar, they may ask you what is the standard deviation. S bar plus square root of 2n. Instead of n, is square root of 2n. Okay, S by square root of 2n is the standard deviation of S chart. Coefficient of variation, I have told you sigma by X bar. Okay, so therefore that is one thing I wanted to remind you in this chapter. That's all for this one. Now we have to move into correlation regression. Shall we have a cup of tea before that? Santosh?
Yeah, we will have the tea break, and
Yeah.
then the topics
Come
are
back after
sampling, correlation, regression are the main topics, and little bit of DOE.
Correlation regression,
Yeah,
and acceptance sampling plan.
right.
We should cover.
Right. So we are at 4 o'clock almost, and we will join at 4:15.
Yeah. 3:58 now. 4:15 you must join.
Right.
Santosh sir,
Yes, sir.
just can we revisit question number 11, because I think there is some small confusion.
I think we will we'll break for tea. Then
Okay.
after the class, we will have just little.
Okay.
I'll then make the necessary,
Or I'll call you, sir. I'll call you.
Yeah, right.
I'll call you right now.
Yeah. So let's go for tea.
I'll call you.
Yeah.
It's so nice of Dr. Subramaniam to sit through. Very good.
Thank you, sir. Thank you.
Meanwhile, acceptance sampling plan, can you, first slide, can you show, Santosh, bring the first slide. You know, all the terminologies and all that are there.